This is the course Engineering Science and the lecture CMOS circuit design. In this particular tutorial, I'm going to show you the basic principles of CMOS circuits. The prerequisites for understanding this course is you need to have a basic understanding of MOSFET operation. That is, you need to know how to turn on and to turn off a MOS transistor. For the NMOS, for example, you need to know that you have to apply a high-level input at the gate electrode, that is a logic 1. And for the PMOS, in order to turn it on, you need to apply a low-level input at the gate, that is a logic 0. In addition, you need to be familiar with the basics of Boolean algebra. Here you need to know the basic logical operations, as for example the inversion, and or, and you need, for example, the De Morgan's law, because we need this for performing basic operations on Boolean equations. Let's go ahead with a simple example. If you're a little bit experienced and you look at this circuit, you will recognize that this circuit is a so-called NOR circuit, which is an inverted OR gate. We will use this circuit to show some important characteristics of CMOS circuits. If you look at the upper part of the circuit, this is the so-called PMOS block. You will see that the transistors within this block are P-type MOSFETs. And if you look at the block in the lower half of the circuit, which is called the NMOS block, you see that the transistors here are N-type MOSFETs. Actually, it's worth to look at one of the transistors in detail. If we look, for example, at transistor T1, we can recognize this transistor as an N-type MOSFET, which means that we have negative charge or electrons which carry the current in the channel right here. So this means the electrons come from the negative pole of the supply voltage, which is ground in this case, and move towards the positive voltage, which is the voltage VB. This means that we can identify this electrode as the source electrode of the MOSFET, and this is the drain electrode of the MOSFET. The input electrode, of course, is the gate electrode, and the bulk electrode, which is not shown here. I can draw the contact to the ground. This is the so-called bulk electrode. In this particular circuit, I left the bulk contacts out for the sake of simplicity, but you should note that for a real circuit, you always have to contact the bulk contacts to ground for the NMOS transistors and to the supply voltage for the PMOS transistors. Next thing which is worth to notice is that we have the same input signal, for example X1 or X2, for both blocks. So if we have X1 going to transistor T4, for example, we have the same signal X1 which goes to the corresponding MOSFET, in this case T1. And the same, of course, applies for X2. This goes to the PMOS block and it goes to the NMOS block. Last thing we should note is that if you look at the PMOS block, here we have, for example, a series connection of transistors. Then you always have the different type of connection here, a parallel connection in the other block, in this case, the NMOS block. So the two blocks, PMOS and NMOS, are kind of complementary, which actually gives this technology its name. So we are talking about complementary MOS technology, or simply CMOS technology. Now we can derive the Boolean equation or the logic equation describing this particular circuit. We can do this by looking at either the PMOS block or the NMOS block. Here we will do both. We will start with the PMOS block, and if we look at the PMOS block tells us when the output signal, and in this case this is the variable y, when the output variable is connected to the supply voltage VB. So if we have a conducting path through the PMOS block, in this case transistor T3 and T4 have to be turned on, then we have a high level output or a logic 1. So we can start writing the equation for the PMOS block. We have a high level output, or y equals, and then we have to write down the condition. So x1 has to be 0. We need a low level at the PMOS transistor in order to turn it on, and we need to have the same, a low level at input x2. This is the Boolean equation describing the PMOS block. So we can, doing a simple operation with this equation, we write again xy equals, and now we can apply the already mentioned De Morgan's law. This gives us x1 or x2 inverted. So from here to here, the way is using De Morgan's law. Now let's do the same with the NMOS block. If we look at the NMOS block tells us when the output Y is connected to ground. This is the case if either transistor T1 or T2 is turned on. So we can simply write down the equation. The output Y is 0, which we note with Y bar, and this is equal to x1 or x2. So this equation tells us the output is 0 if either x1 or x2 equals 0. We can do a simple logical operation on this equation too. So inverting the equation on both sides, of course, yields y equals x1 or x2 inverted, which of course is the same equation we got for the PMOS block. So both blocks, the PMOS block and the NMOS block, are described by the same Boolean equation. If we now look at the resulting equation, it can be seen that this equation finally proves that the circuit on the left is indeed a NOR gate. One last remark concerning the complementary of the circuit. If we look at the PMOS block, for example, and let's assume we have a conducting path through the PMOS block, then it can be shown that there is no conducting path through the NMOS block. The same applies the other way around. If the NMOS block is conducting, the PMOS block is turned off. This means two things. First is that the output Y is always connected to either the supply voltage or ground, but it will never float, which means that we have always a defined output signal, logic high or logic low, in a circuit. Second, it will never occur that we have a conducting path through both blocks at the same time. This, of course, would create a short between the supply voltage and ground and would definitely blow up the circuit. That's also something you don't want to have in integrated circuits. So this is basically all you need to know concerning the design of CMOS circuits, and it means that you should continue with tutorial 1.2.